Hello, dear students. Welcome to the channel and welcome to this new video series in which we are going to discuss about microprocessor and microcontroller subject. It is a subject being offered in the 6th and sometimes in 5th semester of electrical engineering. It is also being offered in EC engineering at some point in some institutes as well. So we are going to discuss that subject today. And to tell you, initially I'm not going to discuss about the very basic fundamentals of microprocessor and microcontrollers. If you want me to cover that, please mention that in the comment section below. If I will receive enough comments, I will be covering it as well. But for today, we are going to start the proceedings from the microcontroller 8085, sorry, microprocessor 8085. And today we are going to discuss about not pin diagram but the bus operation and the memory allocation of the 8085. And if you want to check out the video related to the architecture, so Jaideep sir has already made it and we have shared it with class yesterday, so you can check that one out as well. Meanwhile, without wasting any time, let's get to our subject. So we are going to discuss the initiated operations of 8085 microprocessor and the bus organizations. So if you are studying microprocessor unit, you must have the idea that there are two types of buses in microprocessor: address bus and data bus, right? If you don't, then no need to worry, I will be explaining it. But come to this diagram first and see. Microprocessor operates in four kind of operations. There are four type of major operations in the microprocessor. First one is memory read operation. You can see arrows going here to there, here to there. I will explain, no worries. Second one is memory write, memory read and memory write, first two, and input output read and input output write, right? Yeah. So this is my microprocessor. We will be seeing the pin diagram of it in probably next class. But for now, know that the buses the bus arrangement or the pin arrangement from A0 to A15 stands for the address bus of the microprocessor, and the pin arrangement of D0 to D7 stands for the data bus. Okay. Then there is a control bus going separately, but that's a discussion for some other day, not in detail, but a little bit of glance that I will be providing to you. Now see, the address bus distributes address to memory, to the input and to the output. See, and then it moves forward. About the data bus, see, address bus is unidirectional. It only provides, right? It does not take anything from anyone. But see the data bus going here. It is receiving and providing data with memory. It is providing and receiving data from input, and it is providing data to output, because output well, output does not provide because it is output, right? Sometimes we have the feedback loop, but right now we are going to discuss with the very basic loops, not in detail. So two type of buses, four type of operations or primary operations. See here as well, they have written memory read. It reads the data or instructions from memory, very basic. Memory write, it writes the data or instructions into the memory, again very basic. IO read, it accepts the data from input devices, right? Input devices, what do the input devices do? It gives you the data, and IO read accepts it because it is reading it. And IO write, it sends the data to output device. Now these four operations combined forms the cycle. That cycle is called communication cycle or the communication process. which takes place between microprocessor unit and the memory device. And if my microprocessor wants to communicate with one of the memory devices, it needs to perform few operations, and you can divide those operations in different stages. Here they have divided the operations in three stages. First stage is identifying the peripheral or the memory location. We are not going to use the word peripheral, just because just to avoid the confusion, we are going to use the word memory location. So first we have to identify the memory location, which means we have to identify the address of particular memory location, right? I will be explaining how do you find the address of particular location. Then we have to transfer the binary information, data and instructions. And after providing the binary information, transferring of binary information, you provide the timing or synchronization of the signal. So my microprocessor unit, the 8085, it performs these functions using three set of computation lines, and these lines are called buses: address bus, data bus, and control bus. Here they are. And cumulatively, all three buses are called system bus, right? When we show all three buses as one bus, they are called system bus. So what is address bus? So address bus is a group of 16 lines, generally identified as A0 to A15. As I said, address bus goes from A0 to A15. That's the pen. That's the number of pins. It holds 16 pins in total, A0 to A15. And as I was told you earlier, see, address bus is unidirectional. It does not receive; it only provides. So the bits flow in one direction only, from microprocessor unit to peripheral devices or to memory locations. The microprocessor unit uses address bus to perform the first function. What is the first function? Remember, it it identifies the memory location. Then each memory location, once we identify each memory location by uh, identify each memory location with the use of address bus, memory location by binary number called address um, is identified, right? And address bus is used to carry 16-bit address. That's why it has 16 pins like A0 to A15. So it's very similar to the address of your house, right? Your house can be identified by a number of schemes. For example, 32 Bleecker Street, right? 52 Bleecker Street. It can be in a lane identified by two digits of numbers or four-digit numbers, right? 4535 times square. So when you have only two digit numbers, you can identify only certain houses, around 99 to 100 houses. But when you have four-digit numbers, you can identify around 1,000 houses. So bigger the number, bigger the memory locations to identify. And considering that we have 16 bits, we have very vast um, possible numbers of memory location that we can identify. Then that's what they have written. If you want to see, yeah. So the number of address lines in microprocessor unit determine its capacity to identify different memory locations on peripherals. And the microprocessor unit with its 16 address lines is capable of addressing 2 raised to 16, which totals 65,536, or generally known as 64K memory locations. So most of the 8-bit microprocessors have 16 address lines, and that explains why micro computer system is based on 8-bit microprocessor have 64K memory. So if if you have seen the old floppy disks or the old devices for used for storage purposes, they would be totally based on that. recent times also, you see the storage capability in your phones would be based on the power of 2, right? You have 16 GB internal storage, you have 64 GB internal storage, you have 128 GB internal storage, right? Or the memory cards or pen drives, if somebody still uses them, they are based on 2 raised to power of n, and based on that you divide the memory, right? If you would see, you would find 2 GB pen drive, 1 GB pen drive, 4 GB pen drive. So when I go 2 raised to 0, it becomes 1 GB pen drive. When I go 2 raised to 1, it becomes 2 GB pen drive. 2 raised to 2, 4 GB. 2 raised to 3, 8 GB. 2 raised to 4, 16 GB. 2 raised to 5, 32 GB. 2 raised to 6, 64 GB. So and so on. So that is how the total size of your memory storage device are calculated. So number of address lines is arbitrary. It is determined by the designer of the microprocessor based on such consideration as availability of pins and intended application of the processor, right? For example, Intel 80888 processor has 20 and the Pentium processor has 32 address lines. Now nobody uses 8088 processor, I think, but we all have seen Pentium, hasn't we? Haven't we? So that was the address bus. Now let's come to the data bus. Data bus is a group of 8 lines used for data flow of the data. And as we saw here, the data bus are bidirectional. They take and give data to memory and input. Yeah, for output it's unidirectional for obvious reasons, because output doesn't give you anything back. So the data flow in both directions between microprocessor unit and memory devices, and the microprocessor unit uses data bus to perform secondary function. What was the secondary function? Transferring binary information. It transfers the binary information, and by the mean of binary information we have zeros and ones, 0011, 0011, 1001, 0011. Okay, so the 8 data lines enables the microprocessor unit to manipulate 8-bit data ranging from 00 to double f. And the 00 to double f is by the way hexagonal hexadecimal system, not hexagonal, hexadecimal system, in which we go from 0 to double f. We go in a conventional manner from 0 to 9, and for 10 we write a, and so on, right? A B C D E F. So we go from 0 to 9. For 10 we write A, 11 we write B, 12 we write C, 13 we write D, 14 we write E, and 16 we write F. And when you go from 00 to double F, it will be total 256 numbers, 2 raised to 8. The largest number that can appear on the data bus is double F, which translates to, in binary, this number. I'm not going to count how many number of ones we have here. The 8085, known as the 8-bit microprocessor, and microprocessors such as the Intel 8086, Zilog Z8000, the Motorola C68000, they all have 16 data lines, and thus they are known as 16-bit microprocessor. Then the processors like Intel 30386 by 486 have 32 data lines, and thus they are called 32-bit microprocessor. So next time you go out to purchase a microprocessor, and if you're confused about 32 or 64, just see the data bus, you would understand. Third bus which I wanted to discuss would be the control bus. It comprises of various single line that carry synchronized signals. See, single lines that carry synchronized signals, nothing else. It just gives the synchronized signal to every single one. So the term bus in relation to the control signal is somewhat confusing because these are not group of lines that like address a data bus, but individual lines that provide pulse to indicate the microprocessing unit interface. So the microprocessing unit generates specific control signals for every operation. It can be memory read, it can be memory write, whatever it performs. And these signals are used to identify if a device is performing memory read or memory write operation. Right? What does the device wants to communicate? What does the microprocessing unit intends to communicate? And in order to communicate with memory, for example, to read the instructions from some certain memory location, the microprocessor unit places 16-bit address on the address bus. See here, we have 16-bit address on the address bus. So this is my address bus, and we feed it to the memory decode. We feed it to the memory chip for the decoding process, and the address on the bus is decoded by the external logic circuit, right? And that's how we identify the memory location. Microprocessing unit sends a pulse called memory read because we are reading the memory right now. If we were to write the memory, we would have been sent we would have sent memory write instead of memory read. So the pulse activates the memory chip, and the um, contents of the memory location uh, are placed on the data bus. So whatever content that memory location holds will be placed on the data bus and bought inside the microprocessor. So what happens to the data byte bought into the microprocessing unit depends on the uh, internal architecture of the microprocessor, right? And we will see that internal architecture in upcoming chapters as we understand the microprocessor. Not upcoming chapters in this chapter only, but in upcoming lectures as we move forward in this direction. Now let's see the how the data operates internally. Let me, yeah. So the internal architecture of 8085 microprocessor determines how and what operation can be performed with the data. And what are these operations? So there are five types of operations basically. First is to store 8-bit data. We have different registers for that. Second, to perform the arithmetic and logical operations, there is a special register called accumulator in which we perform all those operations and arithmetic and logical operations. Then we can test for conditions. We have if statement. We have the sequence, the execution of instructions, and we can store data temporarily during the execution in the defining read or write memory locations, which is called stack. So that's called stack memory. Now to perform these operations, the microprocessor requires registers, as I've said, to store 8-bit data, an arithmetic logic unit or ALU, a control logic, and internal buses, right? Just to let the information flow from one point to another. And let me show you here. This one is the image which shows you the different type of registers available in 8085 microprocessor. And see what did they say is the function of the registers are described in reference to the five operations when the processor executes following three instructions. The hex code of these instructions are stored in memory locations from 2000H to 2005 as shown in the figure. So see, first first command is mvib 76h, I think we would go on commands later on. Right now it will be too complex for you to understand it, so rather than that I will just simply be explaining the storage storage map or programmable register map here. So how do you remember it? It's a simple process to remember these registers. Just remember A, B, C, D, E and H, L. Okay, A, B, C, D, E, H, L. A is for accumulator. Accumulator is one of the most important and the major register. All the arithmetic and logical operations takes place in the accumulator itself. We use B, C, D, E, H, L for the storage purpose of 8-bit data. So all these registers are 8-bit registers: accumulator, B, C, D, E, H and L, all 8 of them. And then we have the flag registers. It's a totally separate topic to discuss because we have 5 different flags in it, and we are going to discuss each of them in detail. But that is something that comes after we discuss all the different type of registers. We have stack pointer, which we discussed here, the storage of temporary data during execution in the defined read write memory locations. So that gets stored in the stack pointer. It's a 16-bit register. And we have program counter, PC, which is also a 16-bit register, which uh, points down the memory location from one point to another, right? So it's placed fourth, but it's one of the most important it's most important counter here, because the sequencing operation takes place here. So sequencing the execution of instructions takes place here in the program counter itself. And when the processor begins to execute, it places some address, right? If we are taking address 2000h here, so say 2000, it will place that address 2000h on the address bus. H, by the way, stands for the hexadecimal, because we are not following the regular decimal system. We are following hexadecimal system here. So 2000h on address bus, and increments the address into the program counter to 2000 to 2001 for next operation, and it brings the line code 06 and interprets the code, places the address 2001 on the address bus, and then gets the byte 78h to increment the address in the program counter to 2002. And then it repeats the same process for the next instruction, whatever comes. I'm not going to discuss those instructions right now. MVI move, the simple move instruction. Now once the execution part is done, when the processor executes the first 2 instructions, it uses some register. Let's say register B. It can take B, C, D, E, H, L, any one of them. Let's take register B to store 78h, whatever data we have over there. We have 78 here, so I'm taking 78 in 2001. This is the memory location 2001. This is the data in it, 78. So it takes 78 and we would store it. It uses the register B to store 78h and A to store F2h in binary, the first operation, F2h, this one. So when the processor executes the um, instruction, whatever instruction it is, it will be executed in ALU, arithmetic logic unit, and it adds 78h to F2h, because we were executing the add operation here, just because that, no other particular reason. See, we are having add. So add, what does add do? It sums both of them. So we will get the result. So it will replace the F2h, which was previously in accumulator, by 6ah, which is the 16h, which is the total of no, sorry, 6ah, which is the total of total sum of both of them. And it sets the carry flag as described. We will come to carry flag as well. So in this example, the additional operation gets a carry because the sum is larger than the size of accumulator, right? Accumulator is 8 bits and sum is more than 8 bits. So indicate the carry, the processor sets the flip flop called carry flag. We will be discussing the flag registers, and we will be discussing carry flag in that, so no need to worry right now. The fifth and the final operation deals with the concept of the stack. The stack pointer, the 16-bit register used in the memory pointer to identify the stack, the part of read write memory defined and used by the processor for temporary storage purposes of data during the execution purpose only, which we will be studying later on. But for now, let's keep it till here today. We will be seeing upcoming lectures, pin diagram, and everything in upcoming lectures. If you have any doubts or queries, feel free to mention them in the comment section below. I will try to answer them as soon as possible and as many as them possible. Up till then, take care of yourselves. Have a good time. Thank you very much for listening. I'll be seeing you next time. Goodbye for now.